Good morning. Welcome to lecture 15 and 16 on thermodynamics of materials. We are going to discuss electronic heat capacity today. So, electronic heat capacity. Of solids. We have already discussed heat capacity of solids using Einstein equation, and which was later modified by Debye equation. Solids over, but electronic heat capacity was not detected initially. Electronic heat capacity was not detected initially, but later on it was revealed that electrons also absorb heat. So what happens, I tell you, most cases, in most substances, electrons do not absorb heat. Atoms do. So electronic heat capacity was not detected, but in those cases it was not detected. But in metals and some substances, electrons also absorb heat, but this effect is very small. So, so this is actually, first of all, okay, sorry, let me write here. So let me note this here. Note handout for heat capacity. Handout for heat capacity. From handout for heat capacity is given from, what is this called? Lewis and Randall. Lewis and Randall, later edited or say revised by, either give you Itzar and Brewer. Page running 57 to 60, 52 to page 52 to 67. These handouts for heat capacity is given today. Handout for heat capacity is given today. Okay, is given today. Okay, this one thing. So I said what? In most substances, electrons do not absorb energy, heat. Electrons do not absorb heat. But for metals, and hence electronic heat capacity was unnoticed for many years. However, metals do absorb heat. Okay, do absorb heat. This effect, however, in contrast, metals do absorb heat. However, this effect was However, this effect was so small that it was so small that it was not detected. So small that it was not detected. Well, so this is the status with metals. Actually, metals are good conductor of electricity. The 3 electrons of metal carry electricity. So we expect actually heat will be absorbed easily. Even so, the heat absorption by electrons was not prominent. Actually, expectation is that electrons will easily absorb heat since there are 3 electrons. But electrons actually don't absorb heat. It absorb it, but the effect is small. So this actually another thing is actually. So what we said actually this peculiar situation. This peculiar situation was resolved by the quantum theory of a degenerate Fermi-Dirac. This I will not discuss in, okay. I just will mention this Fermi-Dirac gas. Okay. So note, in absence of electronic heat capacity, disregarding the electronic heat capacity, disregarding the small electronic heat capacity, the heat capacity of atoms heat capacity was of substances. These capacities of substances are given by the as we know kinetic energy of the atoms, that is vibrational and translational and rotational, etc. by the kinetic energy of the atoms. So which we have discussed. We have discussed this. Means electronic heat capacity we didn't consider. Small though, but we'll discuss. And metals actually we can detect, but this is also still small. But here you may note, according to that theory, keep on writing this, okay? Can I remove this over? So according to the theory, that I said a moment ago, according to the theory, that is quantum, according to the theory that I discussed, that is quantum theory of degenerate Fermi-Dirac. electronic heat capacity, C electronic, is proportional to first power of temperature. Is proportional to first power, linear with temperature. That is gamma T. Gamma is what? Property of each metal. Gamma is property, characteristic property of each metal. Another important thing is this: electronic heat capacity, which is small, accepted. Okay, I'm very sorry. Actually, at low temperatures, please note this. At low temperatures, electronic heat capacity is gamma T. Okay, first power. It is to be noted. It may be noted that the electronic heat capacity is best detected either at high temperatures or at low temperatures, not at intermediate temperatures. At the high temperature, what happens? High temperatures, I tell you, electronic heat capacity, C electronic increases with temperature. Not following that equation. And that equation for low temperatures. That equation for low temperature, but still rise with temperature. And as a result, CV that we know, CV rises at high temperature. I'm talking of 3 hours. 3 hours is the heat capacity. Rises above 3 hours. Above 3 hours. This is one reason that means Dulong-Petit equation is not valid at low temperature. Dulong-Petit's equation is not valid at high temperature also. We said that at high temperature it is valid, 3 hours. But high temperature, electronic heat capacity we consider, there is a deviation from 3 hours at high temperature even. At low temperatures, of course, there is tremendous deviation, as was shown by Debye equation and Einstein equation. You see, drastically falls from 3 hours, dramatically falls. So, two things about 3 hours, deviation from 3 hours. But here, one explanation is this: why it rises above 3 hours? Small though, but through the electronic heat capacity. Another is high temperature. And another factor may be noted for this deviation. Is what? Is the actually simple harmonic motion I consider, vibrational free energy. Solid metals, vibrational heat capacity, vibrational energy consider. And we consider it is a harmonic oscillator. Means simple harmonic motion, executing simple harmonic motion, but it is atoms do not actually totally follow the simple harmonic motion equation. There is a small departure. So that's why there is actually deviation is caused by actually deviation from the simple harmonic motion behavior, caused by that's why there is by the writing is this anharmonicity. Anharmonicity means deviation from simple harmonic motion of the atomic vibration. So both of of the atomic vibration. So what we said, you may note this. First of all, we have found here is little bit at high temperature, means say above 1000, 2000, it is not still, it is slightly different from 3R, increases over 3R, above 3R, caused by two factors. One is pertinent to our discussion today, electronic heat capacity, which was not considered, so that causes some increase over 3R. Another factor is simple harmonic motion that was considered, that we have understood, is actually not fully executed, is not fully followed. But a simple harmonic motion, you remember, restoring force is proportional to the displacement and works in the opposite direction. That is simple harmonic motion, and there is actually equations obtained from that. So these two factors, this is over, this is about it. And now I want to, okay, this I want to explain why electronic heat capacity is best detected either at high temperature. High temperature is discussed here. Low temperatures, I will tell you. So low temperature, remember this is valid for low temperature, underline. Not for high temperature. Even so, I don't have equation for high temperature, but it will increase linearly. Okay. So now I give you the low temperature. So why low temperature it is so detected at high temperature is detected? Because it makes heat capacity above 3R. Detected. Best detected either at high, not at intermediate temperature, not moderate temperature, no, you cannot detect. A low temperature is interesting. Low temperature is, I tell you what, if you follow that Debye curve or Einstein curve or factual curve, what is this? Recall, last date CV. You recall this? This is your log T. Typically log T because it is your 0, means 1 Kelvin. Then it is 1 means 10 Kelvin. This is 2 means 100 Kelvin. This is 1000 Kelvin and so on. Okay, and so on. 4. So what is this? The curve is like 3, 4, 3R. It is 3R. Dulong Petit 3R. It is here. Yes, sir. Yeah, then at lower temperature regime, like say what? 10. Okay. Explained by Debye and Einstein. Okay. This actually said. And here what I said at high temperature, what I said? Slightly increase. I have to show this somehow. 3R. This is high temperature. High temperature deviation. High temperature deviation. This is low temperature. Drastic level. And for this quantum theory was needed. Okay. And Einstein first and then Debye explained this. What is the equation? I told you, remember Debye equation for this? Last day, let me write here. And here better. CB is, remember last day, proportional to TQ. Alpha TQ, I said before, proportional to TQ. Alpha TQ. Third power of temperature. CB, what CB this is? This CB is vibrational. This total is vibrational. Okay, this one, 3R. At high temperature 3R and then drops. Explain. Equations are given. Quantum equation. Remember CB? Okay. Or U square e to the power U, e to the power U minus 1 square, U is Ag nu by kT, all discussed. So this is alpha T and this is Debye equation. Now you see, this explains the low temperature, right? At low temperatures. So since we are discussing at low temperature, this is relevant. So as temperature, follow this. At temperature, this is electronic. This is what type of CB? This is what type of CB? Tell me. This is vibrational. Vibrational is quantized. Vibrational. Now tell me CB, today CB, electronic is what? Electronic, tell me today is first power. Third power, first power. So when temperature decreases, low temperature I am talking of, maybe this temperature say, 2 Kelvin, 3 Kelvin, 10, 15, 30, 50. At this low temperature, you see, these heat capacity, vibrational, entire atoms, no electron, is falls, drops off as third power of temperature. And these also drops as first power. Which drops faster? More quickly. Which drops faster? This one. So that's why it becomes so small that this becomes prominent now. This is answer. These drops decreases so much that this is also decreases. This decrease also relatively large. Okay, a large, in fact large. I tell you. I'll give you the example. Data relatively prominent. See, CV, copper, and this is copper. So 2 Kelvin. Actually, it is better I actually remove this. It is better this side. CV copper. Okay, one is electronic. Okay, acha CV copper. Acha electronic against total. I'll ask you electronic. What temperature? Electronic total. Okay, electronic total and CV 2 Kelvin. 2 Kelvin. What's our data? 0.00036. What's the unit? Calorie. Okay, this will get in the handout. Calorie, but you can consider gram atom or gram mole per Kelvin, as you know. Calorie, but you can convert into joule, multiplying by 4.2. Now, what is the total? Of total 45, 36. 80% electronic, base detected at low temperature. Base detected at low temperature. Total is what? Total heat capacity comprised of, tell me. One is electronic, vibration. Vibration we know, electron is today injected. You think of vibrational, translational, rotational, vibrational you consider. And translation only for gases. Okay, monatomic. So, diatomic, rotational is there, vibration is there. Atomic, of course, and solids. Okay, liquids I have not discussed. So total comprised of 2 electronic. Total is first is vibrational, and you write here electronic. So you see 80% is electronic of the total heat capacity. How prominent it is. Now in contrast, 30 Kelvin raise the temperature. 30 Kelvin, not very large, but greater than 2 Kelvin. Again CV same. What is this? Electronic is what? You can guess this value. 30 Kelvin. Can anyone tell me this value? I will be very happy. This value, you have some clues there. In value, I can write easily, but you can write also. What is this value? Anyone? Into 15. Because 15 times proportional to temperature. 15 times if I multiply, let me multiply. Point 0.0054, okay? Happy? One 0.54, and this will be what? Total is what? Point, okay? 0.415, etc. You check this. This side, remember. This is 0.005. You will write in third decimal here 0.005. You can remove this third decimal. 0.412 like this. So this you see clearly. Now is it? Now what happens? Of the total, this is not actually. This should be closely. If it is vibration TQ, rise to the rise proportional to TQ rather than T. So TQ will multiply 15 whole cube, but that is the vibration. This is the total. So we are close, 0.415. So now see what is the contribution. Total is 405, 5 out of 400. So it is actually about 5 of 400 per 100 is what? Per 100 it is, okay, 400, 1% maybe. 5 out of 400. 5 out of 400 means 4 and 5 by 400, 5 by 4, 1.25. So between 1 and 2%. What was it was? What it was? Oh, yes. How much it was? Contribution was here? Low temperature. Amartya. What is the contribution? Electronic? What percent? What percent? 80%. 45, 36. So with this we have completed this electronic heat capacity. Next I will consider heat capacity of ideal gas, non-ideal gas. We are still in the heat capacity. We have not done it. Heat capacity we should note that what is the difference between ideal gas and non-ideal gas? There is interatomic force. No, non-ideal gas, there is interatomic force. Attraction between atoms. This force is actually mainly attractive force. Attraction between atoms, molecules. So attractive force. So this attractive force, so attractive force between molecules diminishes as the interatomic distance increases. Force, you know, attraction decreases as the distance decreases. As interatomic or intermolecular or molecular intermolecular distance or distance means separation between molecules increases. And then at low pressure what happens? At low pressure, at P tends to 0, there is an attraction. P tends to a large volume. And what happens?
Attraction becomes always
Becomes? At P tends to why? Why?
because of volume.
The container volume is large. So they get, when the container volume is small, they are crowded. And the distance is small, separation is small. When big container, P tends to the volume of the gas though. A volume of the gas means it requires a container. So container volume or volume of the gas is large, then actually intermolecular separation, intermolecular distance is greater, and you may consider there is no attractive force. So then it tends to behave ideal. So at low pressure we say real gas tends to behave ideal. This is the at P tends to 0. The real gases tend to behave ideally because no interatomic force. Because of the absence of because no interatomic force, okay? Because decreases almost to zero value. Now, even at 1 atmosphere, which is very important to us, atmospheric pressure, the real gases behave closely follow the ideal gas equation. This you note, underline. Even at, later on we'll see, I will often consider ideal gas behavior because 1 atmospheric pressure Ideal gas you may consider approximately closely follow the ideal gas equation. What is that? PV is nRT. Today's lecture you will get from the handout that I have given. Oh, what the book of the thermodynamics. The text, the title of the text is Thermodynamics by Lewis and Randall. Okay, I forgot this to write actually. Get from, okay, this all you get. Okay, anyway, I have given the handout already, given you the references. So this is okay, very good. Then what? Next is heat capacity of next. Remaining what? Liquids. Remember, liquid is most difficult to explain. Is more complicated than structure of liquids. Liquids are more complicated than the structure of the liquid. Liquid structure is more complicated than that of solid or gases, or solids. So theoretical analysis is difficult. Prediction is difficult. So what we do? We rely upon difficult. So we rely upon experiment. When theory is not there, what we count on? Experiments. So we rely on experimental findings, findings for liquid heat capacity. You remember all this? This is all over. Heat capacity. Example, note, this is general finding. And general finding, I tell you, general finding is what? Useful. Heat capacity of liquid is highest. Next is who? Out of liquid, solid and gas. Next is heat capacity of solids. And still, next and lowest is heat capacity of gases. So we may note that. Important. CB or for that matter, CP or CP. Okay, I have to check this. CP maybe. CP I'm writing, don't tell me, CP. You check this with the FRS book. Better handout. But CP of what example? CP will mostly use. You remember CP. Then from CP to CP, how to get the relation? CP minus CP is TB alpha square by beta. CP liquid greater than CP solid. CB it is still maintain CB. It is better. CB solid still greater than CB gas or vapor. Gas or you can write vapor also. Vapor is a gas phase. EG for zinc. Zinc metal. CB liquid is how much? It is 31.4. Unit is, here I am giving unit. Joule per gram mole or gram atom per Kelvin. Happy? Then this is how much? This is 29.7 joule per, okay, same unit. Joule, same unit. And then what it is? Next is, I will ask you this interesting question. If anyone can answer. CB gas, suppose you don't have data. I am not giving yet. Zinc vapor. You know zinc vapor? Zinc liquid solid, zinc liquid, zinc vapor, zinc gas. What is the formula for zinc vapor? Vapor H2O vapor, H2O, water vapor. Zinc vapor, zinc. It is not diatomic. It is not Zn2, Zn. If it is Zn, then can you answer? Most of them try to avoid memorizing as much. I have not memorized, okay? This I have actually rationalized. Why it is the value that I will write. Monatomic gas, go back. Behavior ideal, you don't have any other option. Ideal behavior, monatomic, what is the answer? Cb. I'm sorry, it is CP. Okay, I'm sorry, I'm going to get back. I made a mistake. Please do correct. Please, don't mind. This is CP. That's why I said this. And what is this? Tell me, monatomic how much? I said very easy. Easiest is monatomic ideal gas. That is CP. CP is pi by 2R. Because CP minus, for ideal gas, CP minus CP is R. And TV alpha square by beta is general. You apply alpha and beta for ideal gas, you get R. That I will show you later. So he has correct 5 by 2 R. R is 8 roughly 8.314. So it is about 4 times 21. Okay, 20. Roughly 20. All set. The unit is same. Sorry, CP. So this is with this actually. So at the end, at the conclusion, at the end, at the end, to conclude, general expression for CP, which will be used throughout the course. General expression for CP, note this, is CP is A plus as a function of CP as a function of temperature. CP is A plus BT plus C T to the power minus 2. ABC constants are constants measured experimentally. With this we have completed heat capacity. A plus BT plus C T to the power minus CP as a function, for expression of CP as a function of temperature in fact. CP, you write here as, you remove this, otherwise it is classing as function of temperature. I will ask you, suppose this is the statement, equation. Now for those solids which follows say Dulong-Petit equation. What is the value of CB? CB or CP, actual CP will be slightly greater. 3R, there is no temperature term. Suppose it is 3R. 3R will slightly increase 3 by R, 2R by another value. What is that? What does it mean? How it is expressed here? A is that value, 3R. And these are B and C tends to 0. So this, if it is 3R, strictly 3R or such constant, for 29.7. For some solids here also, CP okay, solids 31. Only says CP is 31. That means how will I fit into this? When it is 30 means 30, A is 31. B and C are negligible. Okay. So remember, this is heat capacity is a very important thermodynamic data, and we will use this data in all thermodynamic problems, most of the thermodynamic problems. Without this, we cannot do well with thermodynamics. Enthalpy, for enthalpy one temperature to another temperature, if you want to find enthalpy change, then heat capacity is required. You will see. Well, you found this DH is CPDT. So CP is involved. So without CP, we cannot do in thermodynamics. So that's why we discuss at length the heat capacity. Don't disregard heat capacity, okay? So so this part is over. And try to understand and use heat capacity. Every thermodynamic problem, you will see heat capacity. Even today's handout, I will give you one handout today, later on. I will discuss this. So this is over electronic heat capacity. So next is, this is totally, come back to the first law. Application. This is okay? Application of the first law of thermodynamics. This is totally different. We have returned to the first law. Application of the first law thermodynamics to the four ideal processes, to the four ideal processes. What are they? Yes. What are the four ideal processes? Oh, you know perhaps. One is isothermal, another is adiabatic, still another constant pressure, and constant volume. These four processes sequentially using n moles of ideal gas as the system. So totally defined fully this problem start. Okay, it will take actually fairly long time. So so what first? First is isothermal. Maybe I write isothermal. Okay, isothermal process. Then isothermal have two segments, reversible and irreversible. Before this, keep it handy. What is handy? First law will be useful. First law is what? Recall. Write that. That will be used often. Every so often, first law. What is that? Tell me. In the differential form, dq the differential form means infinitesimal change. What is the final or q finite change or integrated form? This is integrated form. Recall this. Now, we participate in the discussion. That will help you. That will prepare you these lessons. Okay? Here itself. Isothermal process. First, I consider A. Actually, let me give this since it is 4-1 isothermal process. A is what? Reversible. This is the reversible isothermal. Let me sketch you because I have already discussed isothermal process, how to execute. Cylinder piston arrangement, cylinder piston, all you know. So I am just giving the path. PV, this is the path. Is equal 1. PV is okay. Equation of right here also. Equation of gas. Okay. Equation of state. Can you write this also? This keep this handy. Equation of state is what? Tell me of the system. PV is nRT. Don't hesitate. N moles, I have given you n moles. This is the equation of state. Okay. Next is carry on, continue. Good. Reversible. So what is the reversible path? 1, 2, you know this? Okay, start. What I'll do this, I'll kind of tabulate them, list them. Okay. Giving the all pertinent parameters. What are they? First of all, for example, dq I will try to find. This side, dq is what? dw is what? Two path functions is what? Then tell me delta u. I am sorry, du, the internal energy change in the sub differential format, and dh. As I advised you, what? Always start from differential, then integrated form. Integrated form I will get. We'll find integrated form. The integrated form dq. So start this problem is dq. See, you know, remember how to carry out this. Oh, mark. This is very important, highly important. P1. Tell me. V1 T. Isothermal. P2 V2 T. Isothermal. Okay. This is the initial state and final state. Remember this. Okay. Cylinder piston arrangement. Cylinder piston. I should not repeat this, but since P1, and then this is state 1, this is the state 2. This is what? P1, V1T, P2, V2T. How do you execute? P1 minus dP, this P1 minus 2 dP, finally P2, reversible. Okay, this remember, N moles ideal gas. What is missing here? Anyone detect? Find out. Is anything missing important here? Thermostat. Surrounding. The load is the surrounding. External force. Okay, external things are surrounding. P external, T external, temperature surrounding is what it is, this thermostat. Thermostat for temperature? T. That's why it is maintaining T for the system as well. All, recall this, okay? Recall. I should say recall. Recall, you should know that it was already discussed. Recall. So, quickly, first I attacked any, you have to complete this list. Complete this list, okay? Good boy. So, which is the easiest? Attack the easiest. DW part of the easiest, I should suggest. You tell me, you tell me, you are Somoto. DW will be how much?
P equal to T, T minus T.
Means PdB. For reversible, since reversible, quick answer, PdB. Yes, these are states, I am happy. You have said this. PdB. Any idea about, see, three, you note here, 1, 2, 3. You know any two, the third is no. This you apply. Any two, the third. Don't worry about all three. Two only. So DU is easy. Attack the easiest one. This softest target or softest target. DU. DU is what? 0. Why? Why? Huh? Why? Huh? Why you said? What is the answer? Keep close. Now, repeat this.
So there is no change in temperature.
No?
Presence of thermostat. Internal.
That is true. That is true. But internal is a function of temperature alone, and which is constant here. So no change. So give the answers correctly. I am giving you. So note here. I tell you. Note here. Here also. Here note also. In the this box you actually keep handy. Handy means here always in the cell. Use it. What you will use here? I'm giving you another one. Another one. Okay. Here. What is this? U is a function of temperature alone. Why? For ideal gas. Remember? For ideal gas, we are treating what? System. For ideal gas. Actually, why can you, is there any mathematical? If you have mathematical relation, just for example, then it will be more convincing. Indian is a function of temperature. 3 by 2 RT, U, see, one atom you consider, what is the U? 3 by 2 R, no temperature. U is, CB, no, wrong. U is what? 3 by 2 R. You say R. 3 by 2 RT, CB is 3 by 2 R. Don't confuse. CB is del U del T. Differentiate with temperature, then it is 3 by 2 R. 3 by 2 RT. 3 by 2 RT means is in function of pressure. Volume. T. Only T. For example, CB is 3 by 2. U is a function of temperature. Use this aptly. Use. So this you use freely. U is what? Still function of temperature. So U is function of temperature. Since temperature doesn't change, so U is 0. And H also. Oh, I'm very sorry. U likewise. Sorry, actually, this is getting, the list is getting actually also is function of temperature alone. Similarly, please write this. H is not function of temperature. H is function of temperature alone. Function of temperature. Sorry, alone. So this fencing, you have this. Keep this useful. U is function of temperature alone. H is what? 3 by 2 R. RT, 3 RT, 3 by 2 RT. H is?
U is zero.
Hmm?
It is a function of temperature.
What is that value? Language I don't use. No, answer the question. You answered yourself. You said how? For monatomic gas. For example, simplest. Is okay, inscribe in your mind. U is 3 by 2 RT. Simplest. That will be enough. The function of temperature alone. Over. I've written that. H I will take up. H is what? U is 3 by 2 RT. H is what? You have to answer this question. Or you may. What is that? H is U plus PV. So you go back to your notes and keep updated, keep prepared for the next day's class and the current class. Keep updated. Otherwise, difficult, very difficult. Embarrassment, humiliation, all such things. And first of all, you will not love yourself. You will not like yourself. That you could not answer this. H is U plus PV. PV is RT. These are all molar for 1 mole. That's why, okay, if you n moles, you have to multiply by that. Remember, 3 by 2 RT for 1 mole, for 3 by 2 n RT, you have to give this as 1 gram mole, n gram mole. So, yes, correct. So, 3 by 2 RT plus PV is RT is 5 by 2 RT. This was done. You may check. From which you get CP is 5 by 2 R by differentiating. So, you are happy. So, 5 by 2 RT is again same story. Function of temperature alone. Okay. Let us see. Is strictly diatomic also function of temperature alone? And then you have to explain. Diatomic, suppose Deopam, your Anurag will answer us. What happened? We have monatomic with example. So if I took example of the diatomic gas, what would be your answer? You are also close, sir. What would be that close value? U first. U will answer U, H will automatically. U is how much? For diatomic, what is the U? U? Huh? Oh, don't discuss. See, you should take people. Why are you not preparing every day? Keep updated. Okay, what is the U value? There are 3 translation, 2 rotation. How much difficult it is? So half or 2 into half means RT, 5 by 2 RT. But so then here also same thing, 5 by 2 only temperature. But there is little bit difficulty here. Can you see what is the difficulty? You must have some hesitation. Yes sir, but means some. Can you tell me what is that? Sure, but there is some doubt, sir.
Transmission
Vibration, sir. And that guy is function of temperature. Small though. Small for which case? Small or negligible. Which case? Huh? I am talking about that's diatomic, still in the diatomic. You have a kind of actually circumvented diatomic. Light diatomic molecules. Light hydrogen HCl. See, be prepared. You don't like subjects? You don't love learning any subject? No, you love, then why? But if it is, then which case it is, then it is 0. So no problem, still no problem. See, I am wasting time, I know. But see, I always ask questions so that you will be prepared. Then, but which case it will be, sir, a little bit, which will be, you cannot ignore. What is that case? Heavy diatomic, like bromine, iodine. They are say quantum equation. That quantum equation that I have given you, okay? H nu by T2 by H nu by Kt minus 1, and they from which you give heat capacity, that was used in that vibration was used by Einstein in the solids. Similar. So link up. Don't memorize. This is underline. No, we should not memorize. Just unless you are actually in a dire strait, okay, or like this, or you cannot get rid of this, then only memorize only for quick response only. Correct? Ready to? Ready path, process. What's the name of the process? Let us see. Your name I forget naturally. You forget the subject, I forget the names. Your name. Ayush. Isothermal. Anything, just try to improve the answer. Edit the answer. Correct, but not fully. Isothermal process. Isothermal reversible. Isothermal reversible process. That's why this case. Isothermal reversible process. Okay, 1A2. Start. DQ is what? First law. Handy. Two things out means third thing out. Usually this. Okay. So PDB. Very good, sir. Right here also. In addition, PDB, sir. Oh, DH is also by the same stroke. DU is 0, DH is 0. Over. So one list table is over. Achha, I will tell you here. Achha, I may forget later. Achha, then you complete this list. Complete this list. Finite change list. What is this? Delta U. What is this? Delta H. Happy? Quickly, huh? Then I will note important. Note we will add 2 or 3 terms later on when we, what is this? Later on when we have completed second law, when we have started the second law. Note this, very important. Started the second law, namely which are there? Which are there? Actually, note in bracket. Which are there? I tell you. Entropy will come into picture. So ds, right here. ds. I'm very sorry. ds. I'm writing here. ds. Another will be free energy. dg. And another free energy, Helmholtz free energy. But these two are important. That's why 2 and 3 are da. These 3 will be added. Follow now. So this is actually 4 terms plus 7 terms or 6 terms. Later on, we will same thing I am doing. Like that, this. Find ds. Find dg. Remember. So always connect. Actually, oh, this is the extension of this extension. But that has to be done. Now integrated form. This side is integrated. Integrate means you have to integration. You have to integrate PDB. This perhaps you attract 1 to 2. You know the answer for this is what? Recall. P is nRT by V dV. And since temperature is constant, 1 to 2 means actually you know V1 to V2. 1 to 2 I am writing nRT ln V2 by V1. 100 times done. Q is what? Guess. Q is W. Q. Achha, delta U is what? Delta U. Du is 0. Delta U is also 0. Integration of 0. Q is delta U plus W is this. W is same answer, sir. Over. How long? 2 minutes. Reversible process is over. Next is irreversible. Irreversible process I consider. I am ready to write this. Otherwise, you will not follow this. Can I top? Can I remove the top? It's okay. Bus. 1B then. B is what? Irreversible isothermal. Achha, since irreversible have many options, many ways to execute it, to be executed. You know, finite driving force, any value will do. So what I write here, against, first one is against isothermal. Against, not bad. P external is what? Specify. Finite P external is P2. Remember this, remember I said P2, or maybe still more irreversible I will say. Can anyone remember? Still more irreversible. Think about this, I will use this. First one by one. So I am considering this. What is the path? You know, you are tired quickly and very quickly. B2. Give double arrow to distinguish. Give double arrow. So right here this is reversible. Right here it is irreversible. So what is the path? You just give the path here, that will be very good. What is the path? Tell me. 1, B2. Not bad. All known. I am again removing all this useless. Only I am retaining this 4. DQ, DW, DU, DH. DU, DH. Achha, start one by one. What is this? Remember, against P2 external pressure. So what is DW? P external dV. So P2 dV. And dV is what? Again, since thermostated, no way. No way, no way. dq is what? Again, by the first law, it is dw is p2 dv. Then get the integrated form. Actually, right here, irreversible isothermal, you consider this as B1. B, irreversible isothermal, but 1 means there is another second is coming. First finish this. Second, another irreversible isothermal will consider. Another, still another. Quickly, what is this W? Which is integration. Attack the W. Achha, this is what? These are again P2 dV. Again 1 to 2. You can see the 1 to 2. Okay, straight one. What is this? I'll ask some questions. Tell me answer. P2 is what? Remember constant. I'm writing, giving the answer first. P2 times V2 minus V1. Achha, please follow me. P2 is constant. It's a constant pressure process. Start the problem. It is actual pressure varying P1 to P2. Not constant pressure. It is isothermal process. So then what we are using? But we are using constant. Can you explain this? Can you explain this? Remember this. This is a fallacious. So it is a constant isothermal process. P2 is not. This segment I am trying to get. The work done is here. This expansion, this dV expansion against the P2 once and for all it is P2 P1. Abruptly to P2, right? This is irreversible. This is reversal, this side irreversible. So abruptly, suddenly P2, then no work. Then the work comes pertinent. P2, this is a constant pressure, horizontal line. Happy to? No problem, I hope. So that's why be careful about this part. Because it is not a constant pressure process, it's an isothermal process. So Q is what again? Same way, W. So this part is over. Very good, very fast. Okay, next is what? Next is what can I remove? Let me write. While you write, okay, I don't want to disturb that side. That side. Yeah, B2 now. Removing this, please. Removing this. Sorry, removing this. It's okay. Next is 2. B1. B2 will be what? Irreversible isothermal again. Irreversible. I'm removing this. Now it's just fantastic. Irreversible isothermal. 1, 2. B. Under the category B. Isothermal. Against. Yes. What it can be? P external is what? Let us see. What? P1, there is no expansion. Initial pressure and final pressure. P1 remains at equilibrium. Initial state. Maximum degree of irreversibility. A special case. Zero pressure, vacuum. Free expansion. Okay? So remember this. This is the maximum degree of irreversibility. And this is the very common final pressure. I apply final pressure. Final driving force. This is also maximum driving force because 0. P external is 0. What is this? This is called free expansion. Or what is the another name? Expansion. That is expansion against vacuum. Against vacuum. Happy? So good. This, what is the path? Path I am showing by a colored chalk. I am drawing here. So, start. This is the 0 to. This is 0 pressure. 0 pressure. So, how will you get fall? P1, I am not showing here. P1 absorbed to 0. How will you show this? This way, this hits the 0 value. Then it turns. Expansion, required expansion. And what is the name? 1B, maybe C, D, 2. So give the name 1. Give a name this. What is the path? 1, B, C, D, 2. Not bad. Okay, so start quickly. So again, same. Over this you know very well. Okay. Yo, how to carry out this? Very good, very good. If it is zero pressure, it will go where? Given temperature T. What if zero pressure? What is the volume? Infinity. But how can it be content to in the volume V2? How can content? It should be infinity. But you say final volume is V2. How is it possible, sir? Then we actually arrestor arrangement by providing arrestor. Right here, provide arrestor so that volume is final volume. Volume is V2. Is actually is V2. Is V2. Okay, arrestor so that the final arrestor so that final volume is V2. Means volume cannot exceed that. It tries to exceed, go to, but it will arrestor is what? Arrestor, you know. Some extension here into the cylinder, and then bar is there, okay, so that it hits against this latch. Final is content. It is content maybe. He cannot get past. Good, start. Again, it's the same story, same. So start. So final state is equilibrium state. Final state is this latch arrangement. Okay. Arrestor, I'll show you arrestor. Arrestor, you know, arrestor. Okay. So I show this arrestor. I'm showing you. One, arrestor is important. Two, how? Oh, sorry. First, you give arrestor here. Arrestor. Rigid arrestor. So state 2. At volume V2, there is the arrestor. So what is this state 1? This is the gas, state 1. So, thermostat. This arrangement. Pre-expansion. Okay. Here it is a cylinder. P1. Right here, pre-expansion. Okay. Pre-expansion situation. Expansion diagram. Arrestor provided. These are arrestor right here. Arrestor, which will arrest the volume increase. Arrestor. What is happening? Follow me. What is the pressure you are doing here? Pre-expansion. Initial state is initial state. What is that? Tell me. P1. Initial state is so no problem. Final state. Final state likewise here. Also. Pressure is what? P1 to what pressure? 0. Then volume you have content too. Temperature is same. Volume is same. Final state. P2 to P2. So it is P2. No way. Because this is an equilibrium state. P2. So remember one thing here. I should not write so many things. The system is in equilibrium in the final state also. So here. See? Final state. Equilibrium. Now question is here, see here difference between this and this. Here final external pressure is P2, irreversible case, previous one. External pressure is P1 to P2, final pressure is P2, equalization of external pressure and system pressure, irreversible also in the final state, which is an equilibrium state. In the reversible always same. But here, note this point, that it is, what is the inside pressure? At the final state, P2. What is the external pressure? 0. So imbalance. How will you call this? What is it called? How will you call this equilibrium state? Criterion is P system is P surrounding, T system is T surrounding. Okay, all these things I said. Okay, but here remember that is true when there is free interaction, freely interact. But there is no free interaction. This is rigid wall is obstacle. That is freely interact. So that's why we say cylindrical, weightless, okay, piston, okay, weightless and this, okay, frictionless, weightless, etc. So there is no no barrier, but extra barrier. For example, this room may be air conditioned, outside is room temperature. It may, because this is insulator, this is barrier, no free heat interaction. If free interaction, the same temperature. Careful this one. Okay, this is possible. This is still second. Okay, though P surroundings is different from the P system, but still it is system is in equilibrium state and will follow the equation of state, namely PV is nRT. So last final state is also PV is nRT. Thank you very much. These are the few things for mental okay, exercise. Good boy. So start again. Again same story. dq, dw, du, dh. Quickly. Your name is what? Your name I forgot. No. Huh? Pundato. Pundato will tell us. Du is what? Du. This last one. This one. This part. Du. It change. Internal energy change. In the how much? Again, see, gas is ideal gas. It has not changed its character. So ideal gas internal energy change. Isothermal process. Process is all along isothermal. Follow. Process is all along isothermal. All the time. So du is what? Du is what? Du is isothermal. It's okay? Isothermal? Okay to? dw, I will be happy if anyone answers this. Okay, let me ask. Okay, some of you. Okay. Oh, you are actually Nijor. You're Nijor. What is the dw? Easy, very easy. I ask easy questions. You think it is difficult, and that is the difficulty. That is really the difficulty, that you cannot identify that is an easy question. Most of the times I answer 1 or 0. A student answers are not 10.078 say. 0. Why? P external. No barrier. How there is a credit for work done? No barrier, no obstacle, what the system is doing. Against whom? Against nothing. So no credit, no work done. Like this. Happy? Liquid is dw. Quickly, Q is what? W is what? Delta U is what? These are all 0, all 0, supplementary. All 0. Can I remove this part? I am removing this. One thing you notice, I mark here, Q is 0. What does it mean? Q is 0. No heat interaction. Means no heat transfer. Thermostat is there, but it has no job. It doesn't have to feed any heat. But in this case, in this, no. There was Q. There was some Q, no? Q is W, P2 into P2 minus B. There was some heat. But here, no. Because no work has been done. So, what is the answer of this? That means Q is 0. So, no heat interaction between system and surrounding too. Can I write? I am writing. So, that is no heat interaction between system and surrounding. You know, they are there, but no heat is transferred anyhow, in any direction. Okay. What does it mean? Does it sound like anything else? Sound like no interaction between system and surrounding? Sound like adiabatic. No heat interaction, adiabatic. So it is an isothermal process, but at the same time adiabatic, because of this special case of free expansion. So that is adiabatic in character. So we note in this extra special case of free expansion, the isothermal process is an adiabatic process as well. as well. All set? Okay? Let's start. Remove this. So, one down. Isothermal process is over. Second is what? Start. I remove all these things you don't need. Can I remove? Can I remove whole? Press. Start press. Now, return this. These are general considerations, generally true, okay? Keep this. Next is alone. Okay, state second. What's all right? Adiabatic. And again what? 2, 1 is what? Reversible adiabatic. Reversible adiabatic. Right there? Reversible adiabatic. This is the first time we are considering adiabatic in details. Okay, quickly, let me draw you. Let me draw. So first, how the process is executed, same as isothermal. Interesting. Same as isothermal means about the work interaction part. Same, reversible. Start 1. What is the state? P1, V1. Since nothing is constant, you have to give P1, V1, T1. State 2 is what? So start here. Start. What is the starting configuration? System pressure P1. What is the external? Surrounding load P1. Then how we proceed? Reversible, same way as isothermal. So nothing new. So do same way. What is next? What shall I do next is what? P1 minus dP. Since expansion minus dP, compression plus dP, downward. P1 minus dP. Let me write, since first time I am considering adiabatic, note that this is the first time we are discussing P2 plus dP. P2, it is what? Reversible. Okay, good. What is the final state? Since nothing is constant, P2, V2, T. N moles ideal gas as before. System, and this is thermostat. Oh, your name is what? Your name? Huh? Sahil Akhtar. Sahil Akhtar says thermostat. Where shall I give thermostat? Where shall I give the thermostat? Yeah, a thermostat like this. Thermostat. You are hiding your face. Why? Thermostat, where shall I place around the cylinder? No. Adiabatic is no heat interaction. No thermostat. Insulated, sir. Insulated. Huh? Okay? Insulation. Thermal, like in isolated system. One aspect is same. Insulation part, thermal insulation there. Here also. That is system, isolated system, is process. Thermally insulated. What does it mean? Tell me. What does it mean? DQ is low heat interaction. That means system has to do whatever it does with the help of its own resource. What is that own resource? What is that own resource? System has to do work using its own resource. What is that resource? Internal energy. Okay, because no heat, no support, external support from the surrounding. Because no heat interaction, no heat will be provided. So DQ is happy to quickly. Hey, long story start. Don't waste time. DQ, DW, DU, DH. I'll be very happy if you answer. Fill this table, complete. This is job. Which will be easiest for you? I will be happy. Let us see if you have understood well. Which is the easiest? Oh, DQ, very good, very good. DW, and next is what? Next easiest out of the three. Which is easiest? DW is always very. Why very easy? Why? Reversible, sir. PDB, sir. Reversible PdV, sir. Good boy. I'll expand on this. Du also not very difficult. I tell you, I'm writing something. NCB dt, I said. Now coming to this. Don't worry, don't jump. NCB dt. I said du is NCB dt when under what condition? Remember that. I gave you, you have to come under non-mechanical. No, I'm not writing that. That is understood. Constant volume. But this is not constant volume. So can I write? Entitled to write? Will not. Not first of all. But there are some point there, some provision. What is that provision? For ideal gas. Ideal gas is exempted from this restriction. Ideal gas always you will use du is NCBDT and note here, note, no way, note NCB is applicable, is generally, is normally applicable for a constant volume process. For a constant volume process. And normally for all systems. Normal applicable means for normally, that is for all systems. Okay. And okay, very good. And dH is what? Similarly, NCPDT is ditto for constant pressure process. This was our knowledge previous. But these two relations are always valid for ideal gas. Valid for the ideal gas. You write that for the ideal gas. Irrespective of, write this in detail, irrespective of the path. Irrespective of the path. To be explained later. Why, sir? Later. Note this. Explain later means I am giving the answer. I already gave you answer once, smart answer, because internal energy is a function of temperature alone for ideal gas. Not for other gases or other systems, solid, liquid. Enthalpy is function of temperature. This is the underlying reason. But I will explain this. Okay. So this. Okay. Don't worry. But note this. So I have written. If it is accepted, then I write correctly. Then I will do the integration. He says something. dW is interestingly what is? I know two. I know these two. Then third, this will be also nothing but dq is what? Right here. What is dW? Minus du. Minus du also right means minus then CBDT. If necessary, write this. Write as many as possible for your clarity, for your clarification, for your confidence. Right. Do the integration. Q, W, delta U, delta H. Quickly do the integration. Delta U I am doing. Okay. W I am coming to this. Q is what? Is it 0? Delta U is what? N CB dt. 1 to 2. Remember. Say suppose monatomic ideal gas. What is the CB? You told me a moment ago, or diatomic. 3 by 2 or 5 by 2 or such thing is independent of temperature. That's constant. So outside, if you consider that part, since ideal gas we are discussing, CB monatomic we often consider, so no problem. CB outside. CB is not function of temperature. Similarly, do compute this. NCP dt 1 to 2 is what? NCP T2 minus T1 by the same logic. Okay. So what remains? W. W is what? Integration PdV. 1 to 2. Can we do this integration? See, this is just I'll ask you, this is nothing to do with the thermodynamics. This is pure calculus question. Calculus question is what? Can you do this integration y dx? 1 to 2. Can you do this integration y dx? I'll ask whom? Ask whom? Okay, yes, Somo. I can. Can you do the, give the result? Give the result. Integration of y dx.
Why can we take the first?
Taking as, I will not giving you anything. You can take yourself. You can say, sir, this will be 0. 1 and 2 is same. What? Any answer? Can you integrate? Y dx. PDB, forget. PDB, so you might think that these are different things. Okay, PDB. Y dx. Never. Unless the relationship between y and x is known. Y is equal to? Why is what she says? Suggest.
No, sir, he says that if there is a linear
So that is the dependence. Functionality is known. I mean, without knowing the relation between it cannot. That means similarly PDB cannot be integrated without knowing the relationship between P and B. P and B. That is the path. Without knowing the path. That's why it is called path function. You said na PDB I cannot integrate because I want to know the, I have to know the path. Path dependent answer. So path function I cannot integrate. So that means PDB is not a perfect differential. PDB is not a perfect, not D anything I cannot write. So all these things coming back. Good boy. Acha. So retain this form. We'll take up. We'll integrate this later. Knowing the path. Path we'll find out, but another exercise. But do one thing. W is incidentally, right? Incidentally, what is the W? Tell me from here. Minus, oh, right here. Right here. PDB right here is right here. Here. Insert here is minus D. Is minus D. Okay, happy though. dW is minus D. Minus U. So right here, why are you right? Is minus delta U. What is that? Minus delta U. Delta U is given to you. Either this. So do this N CB T1 minus T2. Happy? So the answers you have got. Answers you have got. N CB T1 minus T2. But PDB integration, this is a very interesting question. So what is the path? Have you noted that I have not drawn the path yet? Reversible path? I am drawing it here. I have not drawn it here, but I will draw soon. What is the path? Okay, let me sketch this. How shall I sketch this? I have to sketch this. Quickly. This is the adiabatic path. This is the reversible adiabatic. P1, V1, T1, T2, B2, T2. Happy? So 1 A2 I have given for this is somewhere. Reversible adiabatic. Give here. Reversible adiabatic. What is the path? 1 A2. Happy to? So remove all these things now. This part is okay. So what is pending here? To show this. You write this. To show here. So next job is to find integration PDB, which is 1 to 2, which we cannot unless we get the relation between PB and what is this? And find PB and to show it equal to NCB T1 minus T2. You try PDB. Now see, you might one thing interesting. Can you tell me? Integration PDB, but note. You might say, note. PDB, note here. Integration PDB, I'm just, suppose you try. Suppose PB relation is not known, but I know the PB is NRT. You didn't think of this? You said PB relation you don't know, but you know PB is NRT. I'm trying that. Let us try. I said that you don't know that. You say you agreed that we don't know. But really you don't know. What do you know? 1 to 2, sir. I can, sir. What, sir? NRT. P is NRT by V dV. I cannot. Now can you integrate? Can you integrate now? Why? Temperature? Not constant. It's a team. It's again same problem. So it is PV functionality not known, PV not known. So problem is actually given in a different shape. The problem shape is changed. NR can be outside, but TB how we integrate? So same. So question. So you cannot unless path equation unless so equation of the path. So next job is remove. Next job is remove all these things. But can I remove this? This I can remove, not this side unnecessary. You are smart now. You are smart. Start. Next is this one to find the equation for the reversible adiabatic path. For the reversible adiabatic path. What is the reversible adiabatic path? Tell me what is the path? One. What is the equation? Quickly, very fast. This is purely mathematical exercise. dq is first law. First law I start. dq is what? Tell me quickly help. 0. Adiabatic 0. Apply the freely we apply the your knowledge and your relationship. Du is what? Du NCBDT irrespective of as long as dw is always PdV reversible. Is it? Underline reversible. Underline here reversible adiabatic path. PdV quickly. Or what sir? NCBDT is minus PdV. What is minus PdV? So minus nRT by VdV. Quickly, NN cancels, sir. Or CBDT by T, sir, is what is this? Minus CBDT minus PdV is nRT by C. So dt by T is what? Minus RdV by V. Good boy. Now integrate minus RdV by V. Integrate between T1 to T2, V1 to V2. Do this or CB ln T2 by T1 is what? Minus is absorbed R ln V1 by V2. Happy? Or start this point. This will remove this. I'm just doing this unnecessary. So this part is all over. This is all over. Okay, so remove this all. Okay, R ln V2. So what is this? Or ln T2 by T1 is what? Is R by CB. ln V1 by V2. R is what? CP minus CV. CP minus CV. Okay. Okay. So what is the? So what it is? ln V1 by V2. Or let me write CP by CV is what? Gamma minus 1 or gamma minus 1 ln V1 by V2 or ln V1 by V2 powered gamma minus 1. Or what is the relation? Or you could say ln cancel. Or T2 V2 to the power gamma minus 1 is T1 V1 to the power gamma minus 1. That's it. That is TV to the power in general constant. This is the equation of the path TV in terms of T and V. But it can be written in terms of P and V also. Okay, so do that job correctly, quickly. Constant. Okay, constant. This is the equation of the path. This is the equation of the path in terms of TV. In terms of TV relation. In terms of PV, our job is PdV integration PdV. We want to do so PV relation. You have to find the PV relation. To find the PV relation quickly. PV relation. Can I remove this all? Quickly, let's do this. PV, T2 is or, T2 is what? P2 V2 by, now you do this. T2 is P2 V2 by R. P2 V2 by R is T2, this one, times V2 to the power, gamma minus 1 is P1, V1 by R, V1 power, gamma minus 1. R cancel. For what you getting? P2 V2 to the power gamma is P1 V1 to the power gamma. That's it. That is here also box. That you are waiting for. Or Pv to the power gamma, I am very sorry, Pv to the power gamma is constant. So what is the equation of the path you write here? Pv to the power gamma is constant. All set? Okay. Now what is work done? Given this, two important issues. So this is you wanted because you have to integrate PdV. Now you got a PV relation. So use this. Okay. Can I remove this all? Oh, I forgotten to tell P. This is the P. This is the V. Remember. Correct figure. Okay. Now start. Oh. Last. So now that take up the job. What is the job? Integration W is PdV 1 to 2. What is the P? Now you write Pv to the power gamma is constant. Call it K. Give a name. Constant K. Say K. Say. Say what is P? Tell me quickly. It is math. Totally math. P is K by V to the power gamma. K by V to the power gamma dV. So what is this? Again, keep on writing. Is what? You write here K V to the power, right here, V to the power minus gamma plus 1 by minus gamma plus 1. Write this. Minus gamma plus 1. Okay, now you need to follow. What is this? I am writing separately. So 1 by 1 minus gamma. Right. What is that? 1 to 2 means V1 to V2. Right. 1 by 1 minus gamma is common. K into V2 to the power minus gamma plus 1. Keep it there, no problem. And minus K into V1 to the power minus gamma plus 1, no problem. Quickly. Next is what I am substituting here for K. You follow clearly. 1 by 1 minus gamma. What is K? In this case, I am using what? Conveniently. K is what? Constant. Means what? What is constant? Is this constant is same as P1 V1 to the power gamma is P2 V2 to the power. All are constant. Okay. So K is what? You write here convert for V2. You write right. K by K is what? Okay. P2. Right. Good. P2 V2 to the power gamma times V2 to the power minus gamma plus 1. Happy? Now remove all these things. Unnecessary. All over. Okay. Minus, this is this part. Minus K, since it is V1 is there, right? P1 to the power gamma times V1 minus gamma plus 1. That's it. So what you are getting? 1 by 1 minus gamma P2 V2 to the power V2 V2 minus P1 V1. So this is actually absorb the minus P1 V1 minus P2 V2 by gamma minus 1. This is all done. So W, this is the W. Okay. All right. First or W is P1 V1 minus P2 V2 by gamma minus 1. Right here. Separate this. W. Okay. Now you have to show the next thing is what? This must be same as. Tell me. Same as CB and CB. Yeah. Showing here. NCB T1 minus. So do this quickly. Do this quickly. Okay. Is what? Right. P1 V1 is what? Tell me quickly. NR T1 minus NR T2. Gamma minus 1 is what? Cp minus Cb by Cb. Cp minus Cb is what? R. R cancel. So what goes up there? R cancel. So what goes there? NCb T1 minus T2 reconciled. So you are all set. Another thing. I forgot to note this. Work done is this. So work done is what? Expansion. So note, important. W is what? Tell me. Okay. Any NCB T1 minus T2 say. Suppose I consider this. Is positive or negative? W take okay. W two ways. W is what? This and this. Okay. You give whole thing box. Two formula. NCB T1 minus T2. I'm picking up this one. Sorry. Careful. Reconciled. Quickly. This is positive or negative? Tell me. How to know the positive or negative work? I told you what? Tell me. Expansion, sir. Against this pressure, system is doing what? Easy to follow. Lifting. Doing what? And you're quizzing. So someone else is doing on it. Easy. Human experience also. Well, it is this gas is expanding against this resistance, this load, external load. Moreover, I told you give actually, what is this called? Actually, thumb rule, quick rule. What is that? Expansion, work done by the system, positive. This is work done by the system. This whole thing that W is what? Work done by the system. So it is positive. It must be positive. Is positive, what does it mean? What does it mean? It was T1 greater than T2. So, or T2 is less than T1 means final temperature is less than, what does it mean? Final temperature is less than, means cooling has occurred. See, follow this. This is cooling, final temperature is less. So this is called adapt. So cooling has occurred due to expansion. Cooling has occurred. What does it mean? So this is called adiabatic cooling. You will study later. There is another cooling, Joule-Thomson cooling, different thing. This is called adiabatic cooling. Can anyone explain this adiabatic cooling? Follow this. This picture. You don't know. Mathematically, you don't know. No. See, cooling temperature will fall as. Thank you. Temperature will fall. Can you please? That temperature will fall from this figure. Conceptually. There are three ways: graphically, conceptually, and the system is doing what? Why temperature falls? Why this gentleman with the temperature T1, when he reaches here in this adiabatic process, cools off? What is the reason? Yes, insulated, no doubt. So,
we cannot take a heat from the thermal.
okay, sure.
And it does the work at the cost of its heat.
At the expense of internal, very good. At the expense of internal energy. So what? Why temperature will fall? At temperature, they are linked up. So there is a fall in internal energy, there is a fall in temperature. Easy. This work is done. You feel that as if you are lifting. This work is done at the expense of no support, external. Heat out. So your own resource, that means your resource is actually internal energy. Internal energy drops, hence temperature. This is the easy way to understand. Both ways. Thank you. So 5 minutes left, na? Okay. So I stop at this stage, since actually no 5 minutes. Okay. So next class I will consider what? Irreversible adiabatic expansion. Next class. So next class. Actually, one thing. Don't still don't. So let me announce here. So announcement. Second announcement is what? What is that? Assignment number 2. Assignment number 2 is handed today. Is given today. Due date. Today is what? 4th. Will be 11th. May 11th. 1 week. Okay, happy though? So all over. Thank you very much. With this, we have actually completed our discussion today. Thank you for your patient hearing. Okay.